Newton's laws of motion are fundamental principles in classical mechanics formulated by Sir Isaac Newton. They describe the relationship between the motion of an object and the forces acting upon it. The laws elucidate concepts such as inertia, acceleration, and action-reaction pairs, providing a basis for understanding mechanical motion. Certainly, here's a brief explanation of each topic related to the laws of motion. Newton's first law of motion. This law states that an object at rest will remain at rest, and an object in motion will continue moving at a constant velocity unless acted upon by a net external force. It introduces the concept of inertia, the tendency of an object to resist changes in its state of motion. Newton's second law of motion. This law defines the relationship between force, mass, and acceleration. The formula is F equals ma backslash, where F is the force applied to an object, m is its mass, and a is the resulting acceleration. This law quantifies how the motion of an object changes when subjected to an external force. Newton's third law of motion. This law states that for every action, there is an equal and opposite reaction. In other words, if object A exerts a force on object B, then object B simultaneously exerts a force of equal magnitude in the opposite direction on object A. This law highlights the interaction between two objects and the symmetry of forces. Friction. Friction is a force that opposes the relative motion or tendency of such motion of two surfaces in contact. It plays a crucial role in understanding and analyzing motion, affecting how objects move on different surfaces. Types of friction include static friction, at rest, kinetic friction, in motion, and rolling friction. Applications of Newton's laws. Real-world applications involve using Newton's laws to analyze and explain various scenarios. For instance, understanding the forces involved in car accidents, the mechanics of sports activities, or the behavior of objects in free fall due to gravity. Applying Newton's laws helps in predicting and explaining motion in different situations. The laws of universal gravitation, proposed by Sir Isaac Newton, define the gravitational force between two masses. These laws state that every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Orbits are trajectories followed by celestial bodies, such as planets or satellites, around a massive object like a star or planet. Governed by the laws of universal gravitation formulated by Isaac Newton, these orbits result from the interplay between gravitational attraction and the object's forward motion. Newton's law states that every mass attracts every other mass with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. In orbit, gravity continuously pulls the object toward the massive body, balancing its inertial tendency to move in a straight line, creating a stable, repeating path. Calculus is a branch of mathematics that explores the concepts of change and motion. It involves studying functions, derivatives, and integrals, providing tools to analyze rates of change, slopes, and areas under curves. Calculus plays a fundamental role in physics, engineering, and various scientific disciplines. Limits and continuity. Limits involve understanding how a function behaves as the input approaches a particular value. Continuity examines whether a function has no abrupt jumps or breaks. These concepts form the foundation for more advanced calculus topics. Derivatives and applications. Derivatives represent the rate of change of a function. They are fundamental in analyzing motion, rates, and slopes. Applications include finding maximum and minimum values, determining velocity and acceleration, and solving optimization problems. Integration and area under curves. Integration is the reverse process of differentiation and involves calculating the area under curves. This is useful in determining accumulated quantities, such as total change, and has applications in physics, economics, and engineering. Differential equations. Differential equations involve functions and their derivatives, playing a vital role in modeling dynamic systems. They are used to describe relationships in various fields, from predicting population growth to analyzing electrical circuits. Multivariable calculus. Multivariable calculus extends calculus to functions of multiple variables. Topics include partial derivatives, which analyze how a function changes with respect to one variable while holding others constant, and multiple integrals, which extend the concept of integration to multiple dimensions. Vector calculus introduces the study of vectors and their derivatives, providing tools for understanding three-dimensional spaces and physical phenomena. Optics is the branch of physics that studies the behavior of light and its interactions with matter. It explores phenomena such as reflection, refraction, and dispersion, and is integral to the design of lenses, mirrors, and optical instruments for imaging and manipulating light. A microscope is an instrument that magnifies small objects, allowing detailed observation of structures not visible to the naked eye. Using lenses to focus light, microscopes find widespread use in biology, medicine, and materials science for tasks ranging from cell examination to quality control and manufacturing. On the other hand, a telescope is an optical device designed to observe distant objects by collecting and magnifying light. Telescopes come in various types, including refracting and reflecting designs. They play a crucial role in astronomy, enabling the observation of celestial bodies such as stars, planets, and galaxies, helping to unravel the mysteries of the universe. A prism is a transparent optical element with flat, polished surfaces that refract and disperse light. It is commonly used to separate white light into its constituent colors through the process of dispersion, revealing the spectrum. Prisms have applications in spectroscopy, photography, and optics. A wave is a disturbance that propagates through a medium, transferring energy without causing permanent displacement of the medium itself. Waves exhibit characteristics like wavelength, frequency, and amplitude, and they occur in various forms, such as electromagnetic waves, sound waves, and water waves. In transverse waves, oscillations occur perpendicular to the direction of wave propagation. Light and electromagnetic waves are classic examples, where the electric and magnetic fields oscillate perpendicular to the direction of the wave's travel. Understanding these wave types is fundamental in comprehending various natural phenomena and technological applications. Longitudinal and transverse refer to the orientations of oscillations in waves. In longitudinal waves, the particles of the medium oscillate parallel to the direction of the wave propagation. Examples include sound waves, where air particles move back and forth in the same direction as the sound wave travels. Electromagnetism is a branch of physics that studies the relationship between electric and magnetic fields. It encompasses the behavior of charged particles, electromagnetic waves, and the interactions between electric currents and magnetic fields. Maxwell's equations provide a fundamental framework for understanding electromagnetism. Electric and magnetic fields are fundamental components of electromagnetism, a branch of physics. An electric field surrounds charged particles, exerting a force on other charged objects within its influence. It's generated by stationary charges or changing electric currents. Magnetic fields, on the other hand, arise from moving charges. They induce forces on magnets or moving charges, and they play a crucial role in electromagnets and devices like transformers. Light, often considered an electromagnetic wave, consists of oscillating electric and magnetic fields perpendicular to each other and the direction of propagation. As light travels, these fields interact, creating the entire spectrum of electromagnetic radiation, from radio waves to gamma rays. Understanding the interplay between electric and magnetic fields is vital in comprehending the behavior of light. Electricity, a flow of electrons, involves the manipulation of electric and magnetic fields. In electrical circuits, current results from the movement of charged particles, generating magnetic fields. Devices like generators and transformers exploit the relationship between electric and magnetic fields to produce, distribute, and transform electrical energy, powering a myriad of technological applications. The intricate connection between electric and magnetic fields is the foundation for numerous technological advancements in our daily lives. Classical mechanics is a branch of physics that studies the motion of objects and the forces acting upon them. It is based on Newton's laws of motion and addresses concepts like kinematics, dynamics, energy, and momentum. Classical mechanics is suitable for describing motion at everyday scales. Kinematics. Kinematics deals with the study of motion, describing the position, velocity, and acceleration of objects without delving into the forces causing the motion. It establishes the fundamental framework for understanding how objects move. Newton's laws of motion. Newton's laws provide the foundation for classical mechanics. The first law states that an object at rest remains at rest, and an object in motion continues in a straight line at a constant velocity unless acted upon by a net external force. The second law relates the force applied to an object to its mass and acceleration. The third law states that every action has an equal and opposite reaction. Work and energy. Work is the product of force and displacement, representing the transfer of energy. The concept of energy is crucial, encompassing kinetic energy, related to motion, and potential energy, related to position. The work-energy theorem links the work done on an object to its change in energy. Linear and angular momentum. Linear momentum is the product of an object's mass and velocity, describing its motion. Angular momentum, on the other hand, pertains to rotating objects. Both are conserved quantities, meaning their total remains constant unless acted upon by external forces. Rotational dynamics. Rotational dynamics extends classical mechanics to objects that rotate around an axis. Torque is introduced as the rotational equivalent of force, and angular acceleration describes changes in the rate of rotation. Conservation of angular momentum explains the behavior of rotating systems, emphasizing the persistence of rotational motion. Fluid mechanics is a branch of physics that studies the behavior of fluids, encompassing both liquids and gases. It explores phenomena such as fluid flow, pressure, and viscosity, providing insights into the dynamics of fluids in motion and their applications in various engineering and natural systems. Fluid mechanics explores the behavior of fluids, encompassing both liquids and gases. Flow refers to the movement of fluids, examining factors like velocity and pressure distributions. Understanding flow is crucial in various engineering applications, from designing pipelines to analyzing weather patterns. Lift, a key concept in aerodynamics, involves the force that enables aircraft to overcome gravity. It results from pressure differences between the upper and lower surfaces of a wing, created as air flows over it. Lift is essential for flight and is influenced by wing shape, angle of attack, and airspeed. Aerodynamics delves into the study of the interaction between objects and air. It encompasses the effects of drag, lift, and other forces on moving bodies. Engineers and designers apply principles from fluid mechanics to optimize the aerodynamic performance of vehicles, buildings, and various structures, enhancing efficiency and safety in diverse applications. Chaos theory is a branch of mathematics and physics that studies complex and unpredictable systems. It explores nonlinear dynamics, sensitivity to initial conditions, and the emergence of intricate patterns. Chaos theory has applications in various fields, including meteorology, biology, and economics, revealing order within apparent randomness. Certainly, here's a brief explanation of each topic in chaos theory. 1. Fractals asterisk. Fractals are intricate, self-replicating patterns that emerge in chaotic systems. These geometric structures exhibit the same complexity at every level of magnification. Chaos theory explores how chaotic systems can produce these fascinating and infinitely detailed patterns, seen in natural phenomena like coastlines, clouds, and even in the behavior of chaotic systems themselves. Bifurcations. Bifurcations represent sudden changes in the behavior of a system as a parameter is adjusted. Chaos theory studies how these bifurcations lead to a cascade of complex and unpredictable dynamics. Small changes in parameters can result in a system transitioning from stable to chaotic behavior, providing insight into the sensitivity of chaotic systems to initial conditions. Strange attractors. In chaotic systems, rather than settling into a stable point, trajectory, or periodic orbit, the system may converge towards a strange attractor. These are complex, non-repeating patterns in phase space that characterize the long-term behavior of chaotic systems. Strange attractors provide a visual representation of the system's dynamics. Sensitive dependence on initial conditions, the butterfly effect. The butterfly effect encapsulates the idea that a small change in the initial conditions of a system can lead to vastly different outcomes over time. Chaos theory explores how tiny variations in the starting state of a chaotic system can amplify into significant and unpredictable deviations in the system's evolution. Chaos in deterministic systems. Contrary to common intuition, chaos can arise in deterministic systems where the future behavior is entirely determined by present conditions. Chaos theory investigates how deterministic systems, governed by precise mathematical equations, can still exhibit sensitive dependence on initial conditions and produce seemingly random and complex behavior over time. Thermodynamics is the branch of physics that deals with the principles governing heat, work, and energy transfer in physical systems. It encompasses concepts like temperature, entropy, and the laws of thermodynamics, providing a framework to understand and analyze the behavior of matter and energy in various processes. In thermodynamics, energy is a fundamental concept representing the ability to do work or transfer heat. It exists in various forms, including kinetic energy related to motion and potential energy associated with position or stored within a system. Thermodynamics explores how energy is transformed and exchanged in physical processes. Temperature is a measure of the average kinetic energy of particles in a system. It quantifies the degree of thermal motion and is crucial in determining the direction of heat flow between objects. The second law of thermodynamics introduces entropy, a measure of the system's disorder or randomness. Processes tend to move towards higher entropy states, reflecting the natural tendency for systems to evolve towards greater disorder. Understanding energy, temperature, and entropy provides a framework for analyzing and predicting the behavior of physical systems in various contexts, from engines to chemical reactions.